This is the current form of the full scroll dial that's now in the hands of about 100 adventurous early adopters. It's been quite a journey, starting from this proof of concept I hacked together one day after I finally cracked from rubbing my finger raw on my scroll wheel. The janky thing worked so well, I immediately knew I had to make a prototype without the dangling ornaments. That video has gotten several views since, so I knew I wasn't alone in my quest for premium scrolling. Of course, this hastily built prototype doesn't qualify as premium, so I completely redesigned version 2 with actually premium components, like a ceramic bearing and an anodized aluminium dial. It was better, but still not good enough. So version 3 was all about experimentation. The double diamond approach, if you will. I stabilized some walnut and built a dial out of it. It looks decent, but it was a huge pain to make. I also tried a whole bunch of other stuff, but I don't want to spoil it for you if you haven't seen the video. Up to now, all the builds have been literally one of a kind, which means I'm the only one enjoying this superior scrolling experience. Not that I'm gloating or anything. So in this video, we'll take all the lessons we've learned and put it into something that people can actually get their hands on. Let's start with the base. This part was printed using a tough resin and required a huge number of print supports. Even though it is pretty satisfying to remove the supports, they don't seem to be doing the best job with dimensional accuracy. So the part needed to be post-processed, which is something I obviously enjoy doing very much. But no amount of post-processing can fix how brittle this material is. To be honest, these aren't the only reasons I don't particularly enjoy resin printing.
It's the smell.
So I abandoned the resin chip and went to FDM. Using the multi-material capabilities of the H2D Bambu Lab sent me, I can print the part out of PETG with PLA supports. PLA doesn't adhere to PETG, so the supports can be printed with zero clearance. That makes printing this kind of thing possible. The obvious drawback is the wastage, although the support is printed with the minimum possible amount of material. The H2D's print quality is really good as far as FDM goes. But things like layer lines and seam lines can't be completely eliminated, even with newer features like scarf seams. There's also the issue of warping when printing thinnish walls, and rounded edges or corners when they're supposed to be sharp. Printing at small layer heights like 0.08mm can help with the surface finish, but it comes at a huge printing time penalty, and it doesn't solve all the problems anyway. But there is a way to solve all these problems. That's right, it's post-processing. I could use this same sanding jig from before, but it would be far too much of a pain. Instead, I print the parts slightly larger, then stick them in my CNC and mill them down to the final size. Easy peasy, right? No. If the print settings and the CNC process settings aren't exactly right, there'll be gaps in the walls, and you end up with things like tear out, massive holes on the surface, or just generally a piece of scrap. It took me more than a few attempts to get something halfway decent. And one of the hacks I had to use was to increase the flow ratio in the walls to force them to be printed solid. When I finally managed to get the planets and the stars to align, I got a smooth surface finish that I can proudly call acceptable. This post-processing method has the added benefit of fixing the warped walls, which adds exactly 0 to the functionality of the device. By the way, I wasn't kidding when I said this took me more than a few attempts, but I think the final result is worth it. In the previous design, the non-slip bottom cover was made by resin printing a skeleton, then over-molding it with silicone. It works unnecessarily well as a non-slip surface, but it's a little too flexible for my liking. So here's the H2D coming to the rescue again. You probably can't tell, but this is also a multi-material part. The actual cover is PETG, but the print supports for the recessed holes have a PLA interface, which allows me to pop them off easily. A weird thing that happens with my PETG prints is that some whitish residue gets deposited on the bottom surface. This stuff can be easily removed mechanically, but as fun as it sounds, I don't really want to spend all day scrubbing these parts. Luckily, I found that a hot air gun makes quick work of the residue. It also takes care of any minor stringing, if there's any. I don't know what this residue is, and why heat makes it disappear, so let me know in the comments if you do. By the way, if you're enjoying this video, please subscribe. Now let's talk about the actual dial for a second. Over the past few prototypes, I've tried using dials made from stabilized walnut, polycarbonate, and anodized aluminium. I reckon the aluminium dial was the best overall, but those screw holes really sucked. So when I had new ones made, I got rid of the holes. So you might be asking, how are the bearings going to be held in place? Well, that's not a problem, because the bearings don't even fit. But seriously, this is actually a feature, not a bug. I designed the aluminium dial to shrink fit onto the bearings. Here, let me demonstrate. I'm using a cheap air fryer set to around 140 degrees Celsius. At this temperature, thermal expansion of the aluminium dial should create sufficient clearance. I stick the dial and the bearing in there for a couple of minutes, and when they emerge, the bearing should already have fallen into the hole. After waiting for it to be as cool as a cucumber, in thermal equilibrium with the surroundings, we can handle it and immediately find that the bearings have completely bound up. That didn't go according to plan. With a ball gauge, we can find out easily enough what the problem is. The internal diameter measures about 51.9mm, which is just a tad undersized. The ceramic bearings are 52mm in diameter, and I specified the ID to be 51.95mm, give or take 25 microns. It isn't easy to hold a tolerance on an unnecessarily anodized surface, so I sent a friendly and understanding message to the CNC people. Here's what they said. If you don't know what a CMM is, it's a coordinate measuring machine. Essentially, an expensive robot for measuring things. What they're really saying is that my primitive measurement methods belong at the bottom of the ocean and that I have no business even thinking about the word metrology. Frankly, they're not entirely wrong. These digital calipers are only good to about 20 microns, and the ball gauge isn't exactly a foolproof piece of kit. But is this setup really completely useless? To find out, I set up a little test. This ceramic bearing's inner diameter should be pretty much dead nuts 40mm. And our measurement is bang on. But hey, maybe it's a fluke. So here's a steel bearing with a 35mm inner diameter, and I would consider that close enough for my purposes. And finally, a cheap 10mm ring gauge. Just look at the number of decimal places on this guy. Bang on again. You get the idea. I'm not going to take a ball gauge to a CMM fight, but I don't want to get gaslit into thinking ball gauges are completely useless either. But there's no use moping about not having a CMM. So I started working on plan B, which was to avoid the problem altogether. The problem with tight tolerances, that is. Because I'm mounting a round object, the solution starts as usual with making soft jaws. I'm really gonna have to order a chuck at some point. With the soft jaws done, I stick the problem child into the vise and give it a good probe. The plan is to expand the inner diameter by 2mm. This CNC router is only slightly more rigid than a boiled egg, so the cuts need to be extremely light. But done correctly, even this floppy CNC can deliver decent results. The extra 2mm allows me to insert a flexible TPU ring with crush ribs, which then allows the ceramic bearing to be press fit without binding up. But of course, things are never that simple, because the dial is now wobbling quite a lot. So now we get to play the blame game. I figured the rudimentary probing procedure I used wasn't giving me an accurate center because high-tech as they seem, these touch probes don't actually trigger uniformly in all directions. That is, there's some pre-travel variation known as lobing. Lobing is an affliction that affects probes using this old-school mechanism. In other words, it primarily affects poor hobbyists like me. This white paper by Renishaw explains why this happens and how you should solve this problem. But for now, we're gonna have to deal with this the poor man's way. The first thing to do is to check that we actually do see this triangular lobing pattern. So I created a fork of BCNC, which is an open source G-code sender, and hacked in a bunch of extra circle probing tools. The upgraded probing sequence starts with a rough probe to approximate the origin and the diameter, and then probes the workpiece n times spread out evenly along the perimeter. This sequence needs to be repeated with the probe rotated 180 degrees. I'll show you why in a bit. On the plot, these probe points look like they form a perfect circle. But they don't. The number beside each point shows the error from the best fit circle, and we're actually looking at over 20 microns in variation. If we plot the error using the polar coordinate system, the triangular error pattern becomes pretty evident. But maybe it's the workpiece that's triangular. So that's why we needed to run the probing sequence again with the probe rotated 180 degrees. If the workpiece is the problem, then both plots should already line up. But they don't. If the probe's the problem, then the plots will be 180 degrees from each other. Which they are. Lobing confirmed. That's cool and all, but it doesn't solve the problem, does it? But it actually does help us, because lobing tells us exactly why we should expect to end up with an offset if we use the basic 4-point probing method with an uncalibrated probe. In fact, rotating the probe 180 degrees should be enough to get the lobing to cancel out. But I reckon the best way is to do the probe rotation and use a high-tech circle fitting algorithm, like the Kanatani hyper-least squares fitting algorithm, which was developed just 15 years ago. This is cutting-edge stuff. So let's find out how much of a difference this makes. The first method uses the basic 8-point probing sequence, including the probe rotation, which takes about a minute to run. And the second method uses 256 probe points with probe rotation and the hyper-least square circle fitting algorithm, which takes about 10 times longer to run. And guess what? They're a whopping 7 microns off from each other. That's like the diameter of a red blood cell. Huge! After wasting all that time, I figured maybe the problem might not be the probing after all. So I probed and cut a new dial. This time, once the cutting was complete, I ran the probing sequence again. And guess what? The origins shifted over 50 microns. I'm pretty sure this means my CNC's z-axis isn't normal to the xy plane. One might even say that it's abnormal. I'll just add this to my list of things to fix. So if my CNC's no good, how am I going to properly expand this pocket? Fortunately, I have just a tool for this exact problem. And this tool starts with an L. That's right, it's legal tender. Sometimes, you just gotta hire a pro. And here's what I got in return for my money. Much better. There's still a 3D printed part in the loop, so I'm not expecting absolutely zero wobble, nor do I need it, but seriously, it's now so minimal I can't even see it with the naked eye. Oh, by the way, I had some new PCBs made and assembled by Next PCB. It doesn't look like it, but these boards are a major upgrade. This is the new board, and this is the previous one. Yeah, I know, they look identical at a glance, but the new boards are using the NRF52833 instead of the NRF52832. That little +1 in the part number means we can actually use the USB-C port for more than just charging. High-resolution scrolling now works via Bluetooth and USB. And as it turns out, high-resolution scrolling is natively supported in many Linux distros. Even though the PCB looks pretty much the same, swapping the microcontroller out is a pretty major modification, so the antenna needs to be tuned again. Last time, I did all the measurements and tuning myself, and you can find the full process on my Patreon page. But this time, I decided to stick with the theme of getting work done by the pros and had Nordic do it instead. They sent me a nice report telling me exactly what needed to be changed, and I just do it. Not by hand, of course. I used the CNC for this. And I'll grudgingly admit that the CNC does do a better job than the hand grinding I did before. Now it's time to show off some of the new toys I got to make my life easier. Like this screw presenter, which is way cooler than it sounds. The mechanism is actually really simple and it's incredibly effective. The screws get dumped onto the rails, and the ones lucky enough to land in the right orientation get transported to the pickup zone by vibrating rails. It's so effective, I had to modify it so it didn't try to feed screws too fast. I used the screw presenter with this cheap automatic screwdriver. It has an adjustable torque limit, which is really clutch, if you get what I mean. I also got this cheap receipt printer, but I've forgotten why. Thermal printers are pretty cool though. Inserting the FFC into its connector is still really finicky, and it's my dearest ambition to replace this with something more suitable for automation. Let me know in the comments if you have any suggestions. I also got these automatic tape dispensers, which might be a little over the top, but life's too short to be cutting tens of pieces of tape by hand. Peeling the backing of double-sided tape is another one of those high dexterity tasks that I would be more than glad to be rid of. Real clutch. I've decided to switch to using these silicone feet, which serve the double duty of being non-slip feet and hiding the screw heads. Inserting these things looks simple enough, but it actually starts to hurt after doing 50 or so. Pressing the bearings and the dial by hand is also not ideal, so I foresee more toys in my immediate future. Assembly is complete. Okay, let's take it out for a spin. This time I'm on Windows and the dial is connected via Bluetooth. High resolution scrolling works perfectly as usual, so scrolling can be simultaneously precise and fast. This means I can now scroll through endless lists of register tables in comfort and style. Well, it doesn't look too comfortable in this demo setup, but you get the idea. We've already shipped a bunch of these dials, and my adventurers seem to be enjoying them. So if you're interested in getting one, check out my Patreon page. I've put the link in the description below. There's just one last thing. I've been thinking about bearings more than anybody really ought to. These are the ceramic bearings that we currently use. They are extremely spinny because they run without lubrication of any kind. This does mean they make some noise during use. Well, it's not any louder than a normal scroll wheel, but it is audible. There's also some clearance between the balls and races, which means they rattle a little bit. But the single biggest issue with these bearings is how sensitive they are to dust and dirt. If you happen to get anything into these bearings, they start to sound like this. That was baking soda, by the way. Of course, they can be cleaned out, but it's not exactly the ideal experience. We can get sealed ceramic bearings, but these seals don't do a particularly good job with sealing, and it has a major impact on the spinniness. So I've started shopping for bearings again. And to cut a long story short, I've gone full circle back to the greased stainless steel bearings. Or was it a full 180? Because these bearings are basically the complete opposite of the ceramic bearings. They aren't spinny, and they are completely silent. They can also handle a fair amount of abuse when it comes to dirt, and the grease prevents the balls from rattling. So a couple of months ago, I made myself a new dial with this, and I've been a guinea pig for this setup ever since. To be honest, my initial impression was that it kinda sucked. But that's because I was already so used to the ceramic bearings. After I kicked the sensitivity up a notch and used it a little more, I actually prefer the stainless steel bearings now. In fact, even though I have both dials ready to go, I find myself reaching for the one with the steel bearings pretty much exclusively. It's completely silent, and the damping for the grease sorta gives me a feeling of extra control. Sure, I'm giving up all that spinniness, but I actually don't miss it, especially with the increased scrolling sensitivity. To put it a different way, the ceramic bearings are like a Formula race car. Fast, loud, and not for everyone. The greased stainless steel bearings are more like a family hatchback. Slower but quieter, and can take a whole lot of abuse. So expect to start seeing more dials with steel bearings in the near future. And if you've enjoyed this video, please subscribe.